Hello everyone. On this video we will continue with our introduction to parametric equations. But this time we will create a parametric equation. Okay. So the one example we're going to use, in your textbooks you may have an example either just like this or similar to it, but this is kind of just a general idea of how you could approach it. Okay, now they're not all the same, so you can't just say, okay, I'll use this one for every cycloid in existence, but it will give you an idea of how you can say, okay, well, this is how I can approach it, this is how I can look at it. Okay, so for this example, we're going to find the parametric equations for the cycloid of a ring. Okay, the ring whose initial point at t equals 0 is touching the ground at a point that we will call P. The ring will roll until that same point P touches the ground again. Okay, so to help you visualize, imagine that we have a ring and it's touching the ground at that point. Okay, so we're going to get that ring and we're going to give it a little push, and that ring is going to roll. So when it's rolling, that point that was right here is now, let's say, right here. Okay, so let's say we're going to keep on rolling, and it's rolling and rolling and rolling. Now, that point that started here is now here. Let's say it's somewhere about here now. Okay, now we're going to imagine it's still rolling some more and rolling again and again and again. And that ring now has a point that's right here. All right, and it's going to keep rolling and rolling along until that point eventually touches the ground again. Okay, so if we follow where that point is, so if we go from here to here to here and all the way back there, that circle there is called a cycloid, or at least the one part of a cycloid. If it keeps rolling over and over and over, that just bounces, then it bounces, then bounces, and keeps on going. But this is just one rotation of a cycloid. Okay, so what we're going to do is we're going to find an equation for the cycloid. Okay, so to do that, we're going to start with one ring on an XY axis. Move that up. Okay, so the X, of course, that's going to be the ground. So we're going to have a ring, and please excuse my drawing if it's not perfectly symmetric, but hopefully you get the idea. Oh, hey, that's pretty good, especially for me. Okay. So for this part of the ring, let's say we pluck one up and we just put that as our point P. Okay, that very point that we followed all the way across as we rolled this ring down on the ground, we'll just decide to put it there. Okay, and that particular point will be our XY. Okay, so for this ring, of course, if it's a ring, it's a perfect circle, and if it's a perfect circle, at some point it has a center and a radius. So let's say this, here's our radius, exactly where it is from the ground. Okay, so that point is touching the ground. Okay, so the first thing we're going to look at, this point and the center we're going to create a little dotted line. I didn't want to have a bunch of dotted lines, so I'm going to have like miniature circles and other ways to make dotted lines. Okay, so what we're going to do is we're going to assign from that center radius all the way to the angle of that point to the center. We're going to make that theta. Okay, we don't know how many degrees it is. We just know we're going to make it theta. Okay, so now looking at this very same circle, if we roll this, let's say right at the origin is our t equals 0. If we rolled it from that spot, then we know that the distance from just under center to that point will match the distance from t equals 0 or the origin to that same point. That's the same amount of ground covered. Okay, so that's the very same length. All right, so now what we're going to do is we're going to look at the point from the center to the height where that point is. Okay, and the reason this helps is because now we have the exact length of our y, and we know exactly where our x is. So this helps. So the distance from the point to just above the center, we're going to call that h. You can call it h, you can call it g, you can call it y. It doesn't matter. We just assign a variable because we have no idea what the value is. Okay, so now from just under the center to the angle from the center to the point, that's theta. But the angle from that point to just above the center, we're going to call that phi. So phi. You can call it phi or phi or phi. I'll just call it phi. Okay, and there's a reason that helps. Because if you look at your point xy, remember this is your xy here. So x, if we really look at it, this is the distance of your x value. Okay, and you look from here to here, that's the distance of your h value. Okay, and the reason this is important is because s is equal to your arc length. So our theta is your arc length. So you remember your arc length all the way to P is the same distance covered. So this is actually equal to your arc length, which is r theta. All right, so just those little details gives us some place to start. That's what's helpful. Okay, so what we're going to do is we're going to keep this handy because we're going to come back to this sketch in a little while. Okay, but we're going to start our calculations on the next page. Okay, oh, so if you're still writing, feel free to press pause, but we're going to just slide this over for a quick second. Okay, yep, I did. Move that sheet out of the way. There. Okay, so looking at this just for a quick second, you can see here that theta plus phi is a straight line. So theta plus phi is equal to 180 degrees or pi. Okay, so we're going to move that right out the way. So we know that theta plus phi is equal to pi. So if we solve for solve for phi, so we subtract theta from both sides, so phi is equal to pi minus theta. Okay, how does that help? Glad you asked. What if we look at sine of phi? We know that sine is equal to opposite over hypotenuse. Okay, so going back to our sketch here, we look at opposite over hypotenuse. What's the opposite of angle phi? That's h over the hypotenuse, which is your radius r. So that's h over r. Okay, so that means sine of phi is equal to h over r. If we multiply both sides by r, that gives us h is equal to r sine of phi. Okay, which again is very important. Now I'll show you why. Our x, this will give us our very first parametric equation. X is equal to r theta, remember it's the entire arc length, so you have r theta minus the h. So if you have r theta minus h, you get your x. So x is equal to r theta minus the h. But we figured out that h is equal to r sine of phi. So that means that x can equal to r theta minus r sine of phi. Okay. So if we go ahead and factor out an r from both of those, so x is equal to r times theta minus sine of phi. Okay? But what did we figure out a little earlier? That phi is equal to pi minus theta. Okay, so that means x is equal to r times theta minus sine of phi of pi minus theta. Oh, I got to close off my, there we go. Okay, so why does this help? Because, let me draw a little box here to separate our notes somewhat. Okay, so why does this help? That is because sine of A minus B is equal to sine A cosine B minus cosine A sine of B. Okay, so that means our sine of pi minus theta, we can change that a little bit. So x is equal to r times theta minus, since it's minus that whole thing, it's sine of pi cosine theta minus cosine pi sine of theta. Okay, so since sine of pi is equal to 0, 0 times cosine of anything is just going to be 0, so that whole term disappears. And cosine of pi is equal to negative 1. So that becomes minus negative is positive, so you have sine of theta, but you still have the minus here. So you end up with x equals r times theta minus sine of theta. Okay, now this gives us our x-coordinate that we can use for our cycloid. Okay. So now what about our y coordinate? Okay. So for that, we go back to the sample sketch that we have, figure out our y coordinate. Okay. So here, y is just the height to the point P. Okay. So we know that y is from the ground goes to R, and from this distance here, which we'll call M. You can call it anything you like, we'll just call it M. Okay, so we know that y is equal to the radius plus the distance M. That gives us the height to that point. So y is equal to R plus M. Okay, so let me move this up. So y is equal to R plus M. Okay, how does that help us? Because we don't know what R is, we don't know what M is. But we're going to use cosine of phi for this one. So let me write that out. Cosine of phi. Remember, cosine of phi is adjacent over hypotenuse. Okay, so bringing back our image, adjacent is M, and the hypotenuse is R. Okay, so you have M over R. Okay, so if we multiply, well, let me go ahead and simplify that. Cosine of phi equals M over R. If we multiply both sides by R, we have M is equal to R cosine of phi. Okay, so that helps a little bit. Okay, so starting right from the beginning of our y equals R plus M, that becomes y equals R plus our M is equal to R cosine phi. Okay, but remember, earlier on, phi is equal to pi minus theta. Okay, so y equals R plus R cosine of pi minus theta. Okay, how does that help? Same way it helped here. But difference is we have cosine of A minus B equals cosine A cosine B plus sine A sine B. Okay, so all those trig formulas you thought you were done with, they're making a comeback. All right, so our cosine of pi minus theta, that now becomes y equals R plus R. Okay, that's cosine of pi, cosine of theta, plus sine of pi, sine of theta. Okay, so we know here that cosine of pi is equal to -1. Sine of pi is equal to 0, so this whole thing just becomes equal to 0. Okay, so you now have -1 times cosine of theta, which is negative cosine of theta, which brings us to y equals R minus R cosine of theta, or if you wanted to, you can make it y equals R times 1 minus cosine of theta. And that gives you your y coordinate. For this cycloid. Okay. So again, this method will give you a place to start when you're looking to create your parametric equations for a cycloid. But it all depends on what cycloid you're looking at. Okay, and again, this is just a way to get your foot in the door. All right, hopefully this made sense, and I will see you on the next video.